Hello and welcome to this video on the ICND1 series. In this video, we will look at IP addressing. We will also look at understanding binary, and then we will try some examples of converting decimal numbers to binary. So let's get started. So what is IP addressing? IP addresses are numbers that are used to uniquely identify devices on the network. So when you have devices on the network and they are running the TCP/IP protocol, the kind of addressing that is used to identify these devices, it is what is called IP addressing. And there are two kinds of IP addresses. We have what is called the IP version 4 address and the IP version 6 address. Now, the IP version 4 address was the addressing scheme that was defined many years ago, and it's a 32-bit address, so it has 32 bits. And what that means is that there are 32 binary digits in an IP version 4 address. Now, IP version 4 addresses are being slowly depreciated, and now we have what is called the IP version 6 addresses. And these are even larger with the 128-bit addresses, and 128 bits means that you can have binary digits up to 128 places in one IP version 6 address. Now, a binary digit is a 1 or a 0, and what that means is that in an IP version 4 address, you'll have 32 ones or zeros, while an IP version 6 address, you will have 128 ones or zeros. Now, it's really difficult for you to express an IP version 4 address in terms of its ones and zeros, because that would just be too long. For instance, you're going to have things like 100110101. Well, that's 1, 2, 3, 4, 5, 6, 7, 8. And then 0011111. You can have 11111101. And 10110011. Now, all these strings of binary digits is just one IP version 4 address. It's going to be really difficult for humans to understand this kind of address. So they are expressed in dotted decimal. And this means that they are expressed in terms of decimal numbers that are separated by dots. So you could have things like 10.28.127.34 as an IP address, and each of these digits represents 8 binary strings. So what it means is that the first 8 bits are in this string, and the next 8 bits are in this string, and the next 8 bits are in this string, and the next 8 bits are in this string. And then you have a full IP version 4 address. We will look at IP version 6 in detail in another video, but what you need to know right now is that IP version 6 addresses are expressed in hexadecimal format. And so the 128 bits are actually reduced to 32 strings of hexadecimal numbers. So now let's just look at binary digits and details. Binary numbers are numbers that have just two states, which is a 0 or a 1. Now, decimal numbers, the numbers that we are used to, are numbers that referred to as base 10 because they have 10 states. So you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And these are the 10 states for a decimal number. But for the binary number, you can only have 0 or 1. So why do we use binary numbers instead of the decimal numbers that we're used to in networking and communication? Because we communicate over wires, which uses electrons or lights. And usually, they have only 2 states, which is 0 or 1. So it's either on or off. It's either there is light on the wire or there is no light on the wire. It has only 2 states, and it's easier for machines to understand these 2 states than for them to have many states, like have 0 to 9. So even if you want to express something like a complex digit, for instance, if you want to express the word Bob, you have to fill each of these characters as a binary string, and the machine would convert it to the ASCII character. So all these characters actually have codes which are called ASCII codes, and that's the American Standard Code for Information Exchange. So these codes are what is converted to binary before it's fed into a computer or machine, and that's what the machine interprets into the characters, and that's how you gamble. So yeah, you have binary numbers, which are zeros and ones. In terms of IP addresses, we have 32 bits of this, and they're expressed in dotted decimal. So if you have the first 8 bits and the second 8 bits and the third 8 bits and the fourth 8 bits all being converted to decimal, and then you have an IP address. So let's pick an IP address, for instance, 192.168.7.25. The way a computer would see this would be all in binary. So 25 would convert it to binary, 7 would be converted to binary, 168 would be converted, and 192 would be converted to binary. Now, it's possible for you to be asked to convert binary to decimal in the CCNA exam. So we need to understand how to convert decimal numbers to binary. And that's what we're going to be looking at now. So let me just clear this screen. When you have a decimal number like 7, for instance, in binary, you only have 2 states. So what you have is you have a 0 and a 1. And so when you're going from 0 to 1, when you get to 1, you move to the next place, which becomes a 2. And then if you want to represent 3 in binary, you're going to have 1, 1 instead of 3. So think of it like in decimal, when you had the hundreds, the tens, and unit, and you want to represent 235, you had to have 2 hundreds, 3 tens, and 5 units. In binary, you only have 2s. So for you to represent 3, you're going to have the unit which is 1 and the unit which is 2. So you have 1, 2, and 1, 1, which will be 3. If you were to have, say, 7, what you're going to have is 1, 1, 1, 2, and 1, 4, which is 7. So how do you know the place? How do you know what this is? You keep just multiplying by 2. So you're placed over 8, 16, 32, 64, 128, 256, etc. So for instance, we know that 7 is 111. What if we want to have the number 19? So we're just going to think about it. What's the biggest number we can find in 19, which is 16? That's a 1. And we take 16 from 19, we have 3. So what's the next number place we can find? It's 2. So for the 8th place, we put 0. For the 4th place, we put 0. And for the 2 place, we put 1. Take away 2. And for the 1 place, we put 1. So 19 in binary is going to be 10011. So let's take another example. What if we had 57? Now, what's the largest number we can find for 57? And that's 32. So that will be a 1. If we take away 32 from 57, what do we have? We have 25. In 25, what's the largest number we can find? It's 16 and 25. So we'll put a 1 here too. If we take away 16 from 25, we're going to get 9. And 9, what's the largest number we can find? That's 8. So we put a 1 in for the place of 8. Take away 8 from 9, we get 1. And 1, what's the largest number we can find? That's 1. So 1 is going to be 1. And then 4 and 2 would be zeros. So 57 would be 1, 1, 1, 0, 0, 1. Now, you can confirm these answers by using the calculator on your PC. But you should note that for the ICND1 exam, calculators will not be allowed. So you have to know this to do this manually. So let's just confirm this. So we have the calculator. What you need to do coming to this is by default in the Windows 7, the calculator is in the scientific view, but you can just go in and change it to the programmer view. And then you can, by its default in decimal, so you can type 57 and then convert it to binary just by clicking binary. And there we can see that we are correct. It's 111001. So what we're going to do now is we're going to take a few exercises, and you can attempt them on your own, or we can work through them together. So if you like, you can pause the video and try to do this on your own. So these are the examples. So try to convert these numbers to binary, and then we'll do them together. So the first thing we're going to do is to define our place values, which is 1, 2, 4, 8, 16, 32, 64, 128.256. I'll stop here. So now you can see that we are just multiplying by 2, right? So now for 25, the highest place value we can see, it's 16. When you subtract that, you have 9. So you put a 1 for 16. Next place value is 8. And you subtract that, you have 1. And you can put just a 1 for 8. And of course, the last one is 1. So all these other ones become zeros. Now for 137, it's a little longer. So I put 137 out. What's the highest place we can see? And that's 128. And what's 137 minus 128? That's 9. So 128 would get a 1. The next place value would be 8. And we get 1. So the next place value would be 1. You get 0. So we put a 1 for 8, a 1 for 1. So the rest of it would be 0. Now for 248, what's the first place value we can see? 128. And that's going to give us, what is this going to give us? 120. So 1. Next place value we can see is 64. And that's going to give us 6 and 5. So 56. So that's 1 here. So from the 56, what's the place value we can see? 32. And that's going to give us 4 and 2, which is 24. And from 24, we can see 16. And that's going to give us 8. And from 8, the place value we can see is another 8. And that's going to give us 0. So 1, 0, 0, 0. So what that means is that for 25, we have 0, 0, 0, 1, 1, 0, 0, 1. Now, when I write like this, or you write it like this, 1, 1, 0, 0, 1, it doesn't matter because the leading zeros are not significant. For 137, the number is 1, 0, 0, 0, 1, 0, 0, 1. And for 248, we have 1, 1, 1, 1, 1, 0, 0, 0. Now, because each decimal number in the IP address represents a digit of binary, it's better for us to represent them as 8 digits. So this will be the standard that you should represent your binary numbers with, 8 digits. So if we have a binary address that was 137.25.25.248, what we are really going to have is 10001001.000110001 .0001101.11111000. So that's how to convert a decimal IP address to the real binary format. And that's the format machine understands. So in this video, we have been able to look at IP addressing, IP version 4 addressing, IP version 6 addressing. We've also been able to look at binary digits. I've taken some examples of binary digits. I would urge you to take as many examples of converting decimal numbers to binary numbers as you can, because that's the foundation for IP addressing. And in the next video, we're going to look at IP version 4 addressing. Thank you very much for watching. Hello and welcome to this video on the ICND1 series. In this video, we're going to talk about IP version 4 addressing. So we're going to look at the IP version 4 address classes. We're going to look at Subnet Masks, and we're going to also look at private IP addressing. So let's get started. So the first thing we want to look at is the IP classes we have in IP version 4. Now, in the last video, we talked about IP addresses, and we said that IP addresses were expressed in dotted decimal format. So we had x.x.x.x, where x is a decimal number. Now, if x is a decimal number, and there are 32 bits here, that means that each of these carries 8 bits. That means that in numbers, here can be from 0 all the way to 255. So the kind of addresses we can have addresses from 0.0.0.0 all the way to 255.255.255.255. Now, these addresses are divided into what are called different classes of addresses. So we have classes A to E. Now, what you need to know about the classes for now is that, first, the addresses that start with 0 are not used. The first class starts from 1, and that's class A. And it goes from 1.0.0.0 all the way to 126.255.255.255. And technically what that means is that you have 1.0.0.0, 1.0.0.1, all the way to 1.0.0.255. And then you go to 1.0.1.0, 1.0.1.1, all the way to 1.0.1.255. And you go all the way till you get to 126.255.255.255. Class B addresses, we have the 128.0.0.0 all the way to 191.255.255.255. And for class C, we have 192.0.0.0 all the way to 223.255.255.255. Now, if you notice, we have exempted the 127 address. So we stopped that 1 to 126 for class A and went to 128 for class B. The 127, when it's used for what is called the local host, so it's used to test your TCP/IP stack. So when you have something like, for example, 127.0.0.1, it basically means you're talking about the machine that you're on. So it's just a local host. An example is if you have a web server in your system and you need to access the web server from a browser, you could just type 127.0.0.1 and you're going to access the web server. The differences in class A, B, and C are in the subnet masks, and we'll just discuss that in a second. Well, class D, which starts from 244.0.0.0 all the way to 239.255.255.255, is actually set aside for what's called multicast. If you remember, multicast is when you send one packet, but it has many destinations, meaning that when you send a packet going to any of these addresses, you're actually sending it to a group. There can be many receivers of that packet. It doesn't uniquely identify one system anymore. It identifies a group of systems. Class C, all the way from 240.0.0.0 to 255.255.255.255, it's actually used for research. So it's just set aside for research. So pretty much what you're going to be dealing with day to day is class A, the class B, and the class C. And now let's look at the differences in the classes. So what is a subnet mask? When you have an IP address, the way the IP address knows what network it's on is by using a subnet mask. So for instance, if I have an IP address that says 171.23.5.7 and the subnet mask says 255.255.0.0, now, the IP address is a 32-bit address. The subnet mask is also a 32-bit address. What a subnet mask says is that wherever you have a 1 in the subnet mask, that's part of the network. And where you ever have a 0, it's part of the unique host address. If we expand 255, we have 111.111.1.1. So you have all ones for the first 2 octets and all zeros for the last 2 octets. 0.0.0.0.0.0. Now, what that means is that the first 2 octets representing the network of this address, while the last 2 octets represent the host. So you could say that this computer is on the 172.23 network. Its unique address is the 5.7. So it's on the same network related to 172.23.0.1. It's on the same network with 172.23.255.234. It's on the same network with anything that starts with 172.23. So that's the concept of subnet masks. It helps you to uniquely identify where your network is and what is your host address. So how does that tie into the classes of IP version 4 addresses? For class A, the default subnet mask is 255.0.0.0. And what that means is that It's just the first octet that defines the network part of the address. So for instance, if you have a class A address like 8.2.2.1, by default, it means that it's on the same network with everybody that has an address that starts with 8. And it has the remaining 24 bits here for the host. That means there can be 2 raised to the power of 24 hosts on this network. And if we use our calculator to check that, we're going to find out there could be about 16.7 million hosts on a particular network that is a class A network. Now that's really too large for a network, because if you imagine a network being a broadcast domain, that means that if any of these 16 million devices actually tries to send a broadcast, then all the 16 million devices are going to get it. I don't really think there's any network that is as large as that. But that's class A. Class B tries to reduce the number of hosts that we have on the network by increasing the number of networks by changing the subnet mask. So we have subnet mask as 255.255.0.0, which means that the first 2 octets represent the network, while the last 2 octets represent the host. So we have something like class B address that is like 139.15.6.5. The 139.15 becomes the network, and the 6.5 is just for the host. So what you would say is that it's part of the 139.15 network. And so if you look at this, then you have 16 bits for networks and 16 bits for hosts. That means that you can have for each network 2 raised to the power of 16 hosts, which is about 65,536. And for class C, we follow where this is the number of hosts that you can have, so that we can increase the number of networks that we can have. So with that, we have 255.255.255.0. And what that simply means is that now you can have just 1 octet for the host. So you can have 2 raised to the power of 8 hosts. And that's going to be about 256 hosts. So for instance, if we have a class C address like 195.17.22.136, it means that the first 3 parts are for the network. So this is on the 195.17.22 network, but the host address is a 136. And what it also means is that you can communicate with any device that starts with the 195.17.22. So in general, for subnet masks, the core concept is that wherever you have a 1, it must match to be in the same network. And wherever you have a 0, it does not have to match. So whenever I have, if I have 2 addresses that are 172.16.2.5 and 172.16.7.20, by default, the above class B addresses, so their mask would be 255.255.0.0. Now, if I have 255.255.0.0 here, these are 1s, so it means that these 2 addresses must match. And these are 0s, means that it didn't have to match. So since these 2 addresses match, then we can say that they're on the same network. Now, it can get a bit more complex than that, and we can look at that when we get into subnetting, but in general, this is how a subnet mask works. Private IP addresses are the addresses that are used internally. They are not routed to the internet. And what this means is that normally, if you route every address to the internet, the IPv4 addresses would not be enough. We saw only about 2 days ago on Twitter that Cisco systems count together for over 10 billion devices that are connected to the internet. Now, with the current IP4 version addressing scheme and the classes, we do not have enough addresses for 10 billion devices. In fact, if we have 2 raised to the power 32, that just takes you to about 4.9 billion. And there's still many devices that will be connected to the internet besides the 10 billion devices. So clearly the IPv4 addresses are not going to be enough. So the way this problem is being solved is through what's called private IP addresses. So what this means is that whenever you have a network, an internal network, the address that are used are what are called private IP addresses, and they're not routed on the global internet. This is done to save IP addresses. So what happens is whenever you have an internal network, depending on the size, you can have a class A address or a class B address or a class C address that is assigned to the internal network. And then those addresses are now converted to global IP addresses. So that way we can save IP addresses. And they are converted through a process known as a NAT, a network address translation. So what really happens is that if you have a network of about 200 users, You can give them a Class C address, a Class C private address. For instance, let's say 192.168.1.0, and the subnet mask would be 255.255.255.0. Now, when these users are going to connect to the internet, they can all be translated to just a few addresses through something called port address translation, which we will talk about as we go along in our Cisco journey. So now we can translate all these 200 users to just about 5 addresses. You've ended up saving 195 of these addresses and making more addresses available for the internet and for things to work. So that's why we have private IP addressing. Internally, if you have ever connected to a network, you might notice that the address scheme is one of these schemes, either a 10 network or a 172 network or 192.168 network. And that's because those are defined private IP address ranges. And they were defined in the RFC 1918 for Class A. You have the 10.0.0.0 network to the 10.255.255.255, meaning you have just one Class A class. Because remember that Class A is just a 255.0.0.0 subnet, which means that anything that begins with the first octet is part of the network. So for Class B, we have 172.16.0.0 to 172.31.255.255. So we have 16 Class B classes. And for Class C, we have anything from 192.168.0.0 all the way to 192.168.255.255. So we have 255 Class C classes because the subnet mask for Class C is 255.255.255.0. Now, you need to memorize these private IP address classes because they might be in the exam, and you need to configure them over and over as you go in your Cisco journey. So in this video, we've been able to look at IPv4 classes. We've also been able to look at subnet masks, and we've been able to look at private IP addresses that we have. Thank you very much for watching. Hello and welcome to this video on the ICND1 series. In this video, we are going to talk about IPv4 subnetting. So we're going to look at subnet masks. We're also going to look at fixed link subnetting, and we're going to take some examples of subnetting. So let's get started. What are subnet masks? Subnet masks are used to identify the network in an IPv4 address. So when you have an IPv4 address and you have a subnet mask, with that subnet mask, you can identify the network part of the address and the host part of the address. So for instance, if I have an IP address that is 192.168.7.0, by default, this is a Class C address, and the subnet mask is 255.255.255.0. What this means is that the first 3 octets form the network part, and the last octet forms the host part. In the subnet mask, the 1s represent the network and the 0s represent the host. So in this case, when we expand the subnet mask to binary, you have the first 3 octets will have 1s, which represent the network, and the 0s will represent the host. Now, whenever you have an IP address with a subnet mask, you can calculate what is called the network address and the broadcast address and of the IP address. And the network address is the first address in a network, while the broadcast address is the last address in the network. So for instance, the range of our 192.168.7 network would be 192.168.7.0 all the way to 192.168.7.255. Now, that means that our network address for this range is 192.168.7.0, while our broadcast address is 192.168.7.255. Now, the broadcast address is very useful because if you send a packet to the broadcast address, you're pretty much sending it to every host on that network. The network address and the broadcast address cannot be assigned to a host. So if you have a host on the network, they can only have an IP address from 192.168.7.1 all the way to 192.168.7.254. So that means that in this network, we only have 254 usable host addresses, even though we have 256 IP addresses. One way to look at it is to say that the number of usable hosts in the network is 2 raised to the power n minus 2, where n is equal to the number of host bits. Now let's move on to fixed link subnetting. Fixed link subnetting is when you try to divide a major classful network into smaller network. So for instance, if you have a class C network, by default, a class C network has 256 hosts. But what if we need a smaller number of hosts and more networks? What if you want to have 16 networks with 16 hosts each? This is an example of when you used fixed link subnetting, because you have equal number of hosts in each of the network. And the way you do this is by adjusting the subnet mask of the IP addresses. So far, we've been expressing the subnet mask in dotted decimal format. For instance, we have been expressing our subnet mask as 255.255.255.0 for class C. Now, there's another way for us to express a subnet mask, and that way is what is called a slash notation. And what that simply means is that we can use a slash to represent the subnet mask by counting the number of bits that are 1. For instance, in this subnet mask, we have 255.255.255.0, meaning that the first 3 octets will be 1s, while the last octet will be 0s. So if we expand it to binary, we would have 1111.1111.1111.1111.0000000000. Now, that means that we have 24 1s and 8 zeros. So if we're going to use the slash notation, then our subnet mask would be a /24. So by default, subnet mask for class C is a /24. For class B's, we know that the subnet mask is 255.255.0.0. And that means that the subnet mask would be a /16 because the first 2 octets will be 1s and there'll be 16 1s. For class A, the subnet mask is 255.0.0.0, and that's going to be a /8 because the first octet is the one that has a 1. Now, this is very useful when you get to fixed link subnetting because we're going to have things like /12 or /29 and things like that. Just counting the number of 1s, and this is very useful for us to get used to converting from the slash notation to the decimal notation or the binary format. Now let's take an example. So now we have a question that says that we should subnet the 10.10.0 network into 6 networks. Now by default, 200.10.10.0 is a class C network, and the default subnet mask is a 24, which is 255.255.255.0. Now, we want to subnet it into 6 networks. There are 4 steps to do this. The first step is to find the number of networks. When I say the number of networks here, you'll be surprised because we already have SID networks. But what this means is find the closest multiple of 2 to the number of networks. So what we're going to do is, again, start from 2 and multiply by 2 till we get to the first number that is above 6. So we're going to start from 2, multiply by 2 to give us 4, multiply 2 to give us 8. And since 8 is greater than 6, we will stop there. The next thing we want to do is to find the number of network bits. And the way to do that is to count the number of 2s that we have, and that's 3. So our network bits would be 3. And then that would tell us how to adjust our subnet mask. So our initial subnet mask was 255.255.255.0. If we convert that to binary, we're going to have 1111.1111. 1111.1111.1111.0000000. Now, since we are trying to subnet this network, What we are concerned with is the host, because the host bits right now uses one network of 256 addresses, and we're trying to subdivide it into different networks. So what we're trying to do is we're trying to reduce the number of host bits so we can have more networks. And since we have determined the number of network bits that we need, which is 3, that means that the first 3 bits will become ones. So this will become 111. So our new subnet mask would actually be 1111.1111.1111.1110.1110.0000. So we know that that would be 255.255.255.something. And to figure out what that is, we can just use our binary placeholders. So we have 128, 64, 32, 16, 8, 4, 2, 1. And we have 111, 0, 0, 0, 0, 0. So if we add that together, we're going to have 128 plus 64 plus 32. And that's going to give us 128 plus 64 is 192 plus 32, that's 244. So our new subnet mask would be 255.255.255.224. So how does that help us to calculate the ranges? The way to calculate the ranges is to pick the block size and increase using the block size. And how do you know the block size? The block size is determined by the number of host bits. And right now we know that the number of host bits would be the number of zeros, which would be 1, 2, 3, 4, 5. So we have 5 host bits. And because we have 5 host bits, our block size will be 2 to raised to the power of 5, which is 32. Now, you might not be able to remember what 2 raised to the power of 5 or 2 raised to the power of 7 is. So another way to look at it is where the last one is from your placeholder, and that's 32. So you know that your block size is 32. So based on this block size, we know that our network would be in increments of 32. So for instance, our first network would be 200.10.10.0. The next one then would be 200.10.10.32. The next one would be 200.10.10.64. The next one would be 200.10.10.96, 128, 160. Next one would be 182. The next one would be 224. So we just keep adding 32 to get the number of networks. Now, if you look at it, we have 1, 2, 3, 4, 5, 6, 7, 8 networks, because the next one will be 256, and 256 is already more than 255, so it's not part of it. Now we have 8 networks. That just shows us the mere fact that we want 6 networks doesn't mean we're going to get 6 networks, because of the fixed length subnet mask, you can only divide the network into powers of 2. So that's why we had to do 2 times 2 times 2 at the beginning, which was 8. Now, the other thing you need to know is that the ranges, so for the first network, we're going to have is 200.10.10.0 all the way to 200.10.10.31, which is a number before 32. And that means that this will be our network address, and this will be our broadcast address. Similarly, for the next network, it will be 200.10.10.32 all the way to 63. The next one will be 64 to 91, and this would make this the network address, and that the broadcast address, and all the way down to 224 to 255. Now, this might be a little fast at the beginning, so we can take more examples, and we're going to spend the next video taking examples of subnetting. So in this video, we've been able to look at subnet masks. We also have been able to look at fixed link subnetting, and we started looking at examples of how to subnet. In the next video, we'll continue right from where we stopped by looking at more examples of subnetting. Thank you very much for watching. Hello and welcome back to this video on the ICND1 series. In the last video, we started looking at subnetting, and this video, we will do some more subnetting examples. So we're going to look at subnetting based on network requirements and host requirements. Now let's get started. So in this question, we were supposed to subnet the network 20.0.0.0/8 into 500 networks. Remember in the last example, we looked at a Class C network and tried to subnet it into some smaller networks. So we're going to use the same approach to subnet a Class A network. So we have 20.0.0.0/8. So what does a /8 mean? A /8 network means that the subnet mask is 8 ones and the rest are zeros. So the subnet mask is 1111, 1111, then 0000, 0000.0000, and 0000.0000. So all we have is 255.0.0.0. So that's our subnet mask for the Class A network. And now we want to subnet it into 500 networks. First thing we want to do is to find the number of networks. Now we have 500 networks. We are trying to find the smallest power of 2 that's bigger than 500. So we have 2 multiplied by 2, which gives us 4, multiplied by 2, which gives us 8, multiplied by 2, which gives us 16, multiplied by 2, which will give us 32, multiplied by 2, which will give us 64, multiplied by 2, which will give us 128, multiplied by 2, which will give us 256, multiplied by 2, which is going to give us 512. Now, 512 is more than 500, so we'll stop. So now let's count the number of 2s that we have to get the number of bits. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, another way to say this is 2 raised to the power of 9 equals 512. But remember that you don't have a calculator for the ICND1 exam. So our number of network bits will be 9. And the next thing to do will be to adjust to the original subnet mask. And how do we adjust the original subnet mask? Remember that we had 255.0.0.0, which we expanded into binary in this binary sequence. So what we're going to do is we're going to increase the number of ones by 9. So we're going to have 1111, 1111, and then another one here. And then the rest of those are going to be zeros. So we're going to have a subnet mask as 1111, 1111, 1111, 1111, and then 10000000, and then all zeros. The first octet will definitely be 255. The next octet is 255. And then for this octet, we have 10000000. And if we use our placeholders, we would find it at 128 because it's the first one. So if we have our placeholders, remember 128, 64, 32, 16, 8, 4, 2, 1. We have 10000000. So that's definitely 128. So our subnet mask will be 255.255.128.0. Now to calculate the network range, we're going to use the number of host bits, and the host bits is here in the third octet, what's the most significant. So if we look at the third octet, we have 7 host bits, and 2 raised to the power 7 is 128, as you can see from our place values. So that means that we have a 128 increment in the third octet. So our network's range will start from 20.0.0.0 to, and the next one will be 20.0.128.0. So how do we know the broadcast address? The broadcast address is the address before the next network address. That's going to be 20.0.127.255, because that's the address right before 20.0.128.0. Now, it's easy to make a mistake and say that it's 20.0.127.0, but that will be wrong. It's actually 20.0.127.255. Now, if you want to look at the amount of hosts that you have in this network, it's actually a lot, because we have 8 bits here and 7 bits here. So you have 2 raised to the power of 13 possible addresses. And when you subtract the network addresses and the broadcast address, you're going to have 2 raised to the power of 13 minus 2 hosts. So I'll use a calculator now. And I know that 2 raised to the power of 13 is 8192. When we subtract 2 from that, you get 8190. So we have 8,190 possible hosts. One thing you need to remember is that subnet masks can be represented in the dotted decimal format or in the slash representation. So we can look at this and say, okay, from here we know that it's 8, 16, and 17. So this is also what is known as a /17 network. Again, you should be familiar with the different representations of the slash notation and the dotted decimal notation because the exam questions will come in any format. Now, let's take a look at another example, but this time we will look at trying to subnet based on hosts. In this example, we have the 200.200.200.0 network, which is by default a Class C network. I want to subnet it into 60 hosts. Again, this is almost the same way we did it for the networks, except that for the host bits, we are going to be adjusting the zeros from the right-hand side. So by default, it's a /24 network, which means that there are 3 octets, which is 255.255.255.0. And when expanding to binary, we have 3 strings of 8 ones. Now for 60 hosts, the first thing we want to do is to find the number of hosts, which is the smallest power of 2 that is greater than 60. So we're going to have 2 multiplied by 2, which is 4, multiplied by 2, which is 8, multiplied by 2, which is 16, multiplied by 2, which is 32, multiplied by 2, which is 64. So we know that the number of hosts is 64. Next thing we want to do is to count the number of bits. And we can just count the number of 2's, which is 1, 2, 3, 4, 5, 6. And I would say this is 2 raised to the power of 6 is 64. For the number of hosts between 2 and raised 6, so we are going to adjust the original subnet mask and adjust the original subnet mask. We're going to expand our subnet mask, which is 1111.1111.1111.000000000. Again, because we are looking at it from a subnetting perspective, we are going to be concerned with the host. And now we're trying to adjust the host. Before we had 8 bits for the host, and now we are trying to reduce it to 6 bits for the host. So we count it from the right-hand side. We have 1, 2, 3, 4, 5, 6, which means that these remaining 2 will now become 1. So our new subnet mask will be 1111.1111.1111.1111.11000000, meaning that we're going from 24 bits to 26 network bits. So our subnet mask is becoming a /26. And when we try to convert it into binary, if we use our placeholders, we have 128, 64, 32, 16, 8, 4, 2, 1, and we have 11000000, which is 128 plus 64. So our subnet mask would become 255.255.255.192. Now, for our network ranges, we already know that we have 6 host bits, and 2 raised to the power of 6 is 64. Another way to remember that is to look at the last value of 1 that we have and look at the placeholder, which is 64. So our network ranges will be in increments of 64. So, for instance, we are going to start with 200.200.200.0, and the next one will be 200.200.200.64. For the first one, the broadcast address would be 200.200.200.63, which is the one number before the new network address. So we know that our ranges will be 200.200.200.0 to 200.200.200.63. The next one will be 200.200.200.64 to 200.200.200.127. Now, there are many formats with which the questions can come out on the exam. So, for instance, you could be asked to find the subnet mask. You could also be asked to find the range. You could be asked to find the broadcast address or the network address. You could be asked to compare the 2 numbers if they are in the same network and things like that. So there are different formats with which you can have subnetting question, and the key is to be familiar with how to manipulate subnets. And that comes from a strong understanding of your binary. So I always urge you to take more time to practice more examples. Now we're just going to look at one more example, and this is a Class B network. What we have is 150.20.0.0/16, and we're trying to divide it into a network of 500 hosts. Now again, we have a requirement with hosts and not with networks, but it's the same concept. the first thing we want to do is to find the smallest power of 2 that's larger than the number of hosts, and that we're just going to keep multiplying by 2. So we're going to say 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32, times 2, which is 64, times 2, which is 128, times 2, which is 256, times 2, which is 512. Now, 512 is more than 500, so we would stop. So we have 512 here. Next thing we want to do is a count. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know that the number of host bits have to be 9. Now we're going to adjust the original subnet mask. How do we adjust the original subnet mask? We look at the subnet mask and it is a 16, which means that we have a 16 one. So we just write that out. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, which is 16. And then the remaining 16 would be zeros. So 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0, 0, 0. Now, we have 9 host bits. And so what's going to happen is that from the right, we're going to count 9 bits, which is up to this, the first 8 bits, and 1 from here. And there will be remain 0, meaning that these other ones will become 1. So we have 1, 1, 1, 1, 1, 1, 1. And then the last one will be a 0. And for the last octet, everything will be 0. So we have 0, 0, 0, 0, 0, 0, 0, 0. So we have been able to reduce the number of host bits from 16 to 9. So we've been able to save 7 extra network bits. And that should tell us that we are going to have 2 raised to the power 7 new network, which is like 128 networks. And from our host bits, each of these networks will have 512 IP addresses. So our new subnet mask would be all ones, and 7 ones. So we have 255.255. When we have 7 ones, let's use our placeholders, which is 128, 64, 32, 16, 8, 4, 2, 1. So we have 1, 1, 1, 1, 1, 1, 1, 0. So 128 plus 64 is 192, plus 32 is 224, plus 16, that becomes 240, plus 8 becomes 248, plus 4, that becomes 252, plus 2 becomes 254. So it's going to be 255.255.254.0. So that's our new subnet mask. And if we want to represent it in the slash notation, we are going to have 8 ones, and 7 ones as 16 plus 7, which is slash 23. We can either say our subnet mask is slash 23 or that is 255.255.254.0. They mean the exactly same thing. For our network ranges, the easiest way to look at it is look at it from the third octet, because that's the octet that has ones and zeros. And we know that we have 1 0, which is 1 host bit. That means in the third octet, we have 1 bit that changes. And 1 bit that would be 2 raised to the power 1, which is 2. So in the third octet, we are going to have it increasing in values of 2. So we're going to have things like 150.20.0.0 for the first one. And then the next one would be 2, so 150.20.2.0. Now, what's the broadcast address for the first range? It's going to be 150.20.1.255. Now, think about it. That means that for the first network, you're going to start at 150.20.0.0 and go to 150.20.0.1 all the way to 150.20.0.255, and then move on to 150.20.1.0, 150.20.1.1, all the way to 150.20.1.255. And they will all be on the same network. And then by the time they get to 150.20.2.0, it goes into a different network, and that's a new network address. And that would end up 150.20.3.255. And the next one will start from 150.20.4.0, which will be a new network address. And if we look at it, this shows us that we have 150.20.0.0 all the way to 255, and 150.20.1.0 all the way to 255. That's about 512 addresses, which is what we calculated at the beginning for the host. Again, when you have 512 addresses, the number of usable addresses would be 512 minus 2, which is 510. So you can only have addresses that can now be assigned to 510 hosts, because the first address is a network number, the last address is a broadcast address. Now, I have a couple of questions for you to practice. So I just urge you to take a pen and a paper and try to, on your own, figure out what the subnet mask and the network ranges would be for these 3 questions. Again, you just need to follow the 4 steps in the video and you'll be able to solve these questions. In this video, we've been able to look at subnetting based on 2 different requirements. The first one is subnetting based on the number of networks that we need, and the second one was subnetting based on the number of hosts that we need. So in the next video, we're going to look at variable length subnetting. We're also going to look at some possible troubleshooting questions with IP addressing. Thank you very much for watching. Hello and welcome back to this video on the ICND1 series. In this video, we are going to look at troubleshooting some IP address problems, and we are also going to look at variable length subnet masks. So let's get started. On the ICND1 exam, you would encounter some troubleshooting questions. For example, some questions will ask you for what is wrong with a particular IP address or why a network is not coming up, and you need to be able to use your knowledge of IP address and subnet mask to be able to figure out what the problem is. So for instance, let's look at this question. In this question, we want to know which of these IP addresses is a valid IP address and which ones are wrong IP addresses. When you look at these 4 IP addresses, they all look like legitimate IP addresses, but you need to look further to be able to figure out which ones are right IP addresses. What the question is really asking is, which of these IP addresses can you assign to a host? And you know that you cannot assign a network addresses and broadcast addresses. So what we're going to do is we're going to find out which of these one is a network address or a broadcast address. Let's look at the first one, 192.168.2.31. The first thing we need to look at is a subnet mask, which is /27. It means that you have 27 bits for the network. And when you have 27 bits for the network, that's 1111, 1111, then 1111, 1111, that's 16, 1111, 1111, 24, and 111, 00000. So this means that we have just 5 bits for the host, and that means that we have 2 raised to the power of 5 number of addresses that we can have in a particular network, which is 32. And that means that for the first network, we will have 192.168.2.0 all the way to 192.168.2.31. And the next one will start from 192.168.2.32. So from this, we can see that 192.168.2.31 is a broadcast address, so it's not a valid IP address. You cannot assign it to a host. If we go to the second question, it's a /26, and that means that it would have 32 minus 26 bits for host, which is 6. When you do 2 raised to the power 6, that's 64. That means that your network address will be 192.168.2.0 and 192.168.2.64 and 192.168.2.128, etc. Now, 2.64 is a network address, so you can't assign it to a host. This is also wrong. Now, the third option says 168.17.0.255/23. Normally, when you see a .255, you would assume that it's a broadcast address, but look at the subnet mask. It's a /23, and what that means is that you have 23 ones. So you have 1, 2, 3, 4, 5, 6, 7, 8 for the first octet, 9, 10, 11, 12, 13, 14, 15, 16 for the second octet, and then 17, 18, 19, 20, 21, 22, 23, and then a 0 in the third octet before you have all zeros in the fourth octet. So what this means is that in the third octet, we have 1 bit for host addresses, and it means that we have 2 raised to the power of 1, which is 2. I'll just clear the screen so we have some more space to work. So for 23, we have 1111, 1111, 1111, 1111. In the third octet, we have 7 ones, 111, 1111, 0, and 0000, So here in the third octet, we have 1 bit, which is 2 raised to the power of 1, which is 2. that means that the network address will increase by 2 in the third octet. So we would have 168.17.0.0. And the next one would be 168.17.2.0. And we'll have 168.17.4.0. And the broadcast address for the first one would be 168.17.1.255. So as we can see, 168.17.0.255 would actually be a valid address because it's between these two addresses, and it's neither a network address nor a broadcast address. So this is a broadcast, and this is a network, but this is a valid address. And then for the last question, this is a 24, just to give you a giveaway. For all 24 networks, they start out at 0 and end out at 255. So we know this is a broadcast address. So for this question, if the option A, B, C, or D, the correct answer would be C. Now let's look at another troubleshooting question. If we have a scenario where we have an IP address to be 192.168.1.33 and a default gateway to be 192.168.1.30, and they are both /28, what is wrong with this scenario? First thing we need to look at is the IP address here. What is the network for this IP address? The way we can find that out is from the subnet mask. A subnet mask is a /28. And that means that you have 28 network bit, 4 host bits. And because we have 4 host bits, that means that in the last octet, we would have 2 raised to the power 4, which is 16. And this means that you have your network in increments of 16 in the last octet. So we're going to have 192.168.1.0 as the first network, and we have 192.168.1.16 for the second, 192.168.1.32, and 192.168.1.48 in the increment of 16, like that. And our broadcast address would be 192.168.1.15, 192.168.1.31, 192.168.1.47, etc. So when we look at the IP address, it's in a network between 192.168.1.32 and 192.168.1.47, while the default gateway is in another network between 192.168.1.116 and 192.168.1.31. So we were to put the network address in, it would be 192.168.1.32/28 as a network address. And this would be 192.168.1.16/28 as a network address. This means that they are totally different networks. And because there are 2 different networks, the host will not be able to communicate with the default gateway, and you will not be able to reach any of the outside networks. So the way to fix this would be to either assign the host an IP address in the same network with the default gateway, or to point the host to a default gateway that is in its own subnet. So this is an example of troubleshooting question that you might face in an ICND1 exam. And the way to solve it is to use the knowledge of subnet masks and IP addressing. Now let's move on to another part of IP version 4 addressing, which is variable length subnet mask. So far in all the examples we have been looking at in IP addressing, we've been looking at subnetting based on just one subnet mask. So we have different networks with the same number of hosts on a network. But what if we wanted to have different networks with different numbers of hosts? For instance, in this example, we have our corporate networks to be a class C network. So in this example, we have the corporate network, 192.168.1.0. And we are supposed to subnet into sales, marketing, accounts, and guests, with sales having 120 hosts, marketing 60 hosts, accounts 30 hosts, and guests 30 hosts. So for each department, we're going to run through our subnetting methods and then determine what subnet mask we're going to use. So for sales, the first thing we want to do is to try to determine the number of hosts, and that's the smallest power of 2 that's greater than 120. So we're going to have 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32, times 2, which is 64, times 2, which is 128. So we stop at 128 because it's greater than 120. And the next thing we're going to do is to count the number of bits, which is 1, 2, 3, 4, 5, 6, 7. And that means we need 7 host bits. Our current subnet mask is /24, which means 24 ones. So we have 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot. Now we have 24, so we have 0, 0, 0, 0, 0, 0, 0, 0. If we want 7 host bits, currently we have 8 host bits. So one of these bits will become a network bit. And that means that our new subnet mask would be 11111111 dot 11111111 dot 11111111. And for the last octet, we have 10000000. So our subnet mask would go from being a /24 to /25. And to get the network range, we know that the number of host bits is 7. So 2 raised to the power 7 would be equal to the number of hosts, which is 128. Another way to check if it's true is to place values for this, which is 128 here. Since the last octet is in multiples of 128, we're going to have 192.168.1.0 for the first network and 192.168.1.128 for the second network, and above /25. Now, this is where it gets different for VLSM. In VLSM, you have to decide which of these 2 subnets you want to assign for sales, and then we now subnet the rest for marketing. So if we pick the first one and say this is going to be for sales, we're now going to try to subnet these further. So now we have a new network, 192.168.1.128/25, and /25 means that our new subnet mask has 25 ones. So for marketing, we need 60 hosts. And for 60 hosts, we're going to try to find the number of host bits that we need. And we can do that by saying 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32, and times 2, which is 64. If we count that, we will have 1, 2, 3, 4, 5, 6. That's 6 bits. And that means that we are going to subnet once more. So we are going to be reducing our host bits further by another 1 bit. So we're now going to have 6 host bits. And to get the number of hosts that we needed was 2 raised to the power 6, which is 64. So we know that if the first one is 128, the next one would be 192.168.1.192. But this time it's going to be /26 and 26. And in other words, from what we can see here is that 1/24 network equals 2/25 networks. Also that 1/25 networks can be further subnetted into 2/26 networks. So again, we are going to pick which one we want to use for marketing. And we're going to say, that's okay. Let's assign the first one to marketing, which is this /26. And then we're going to further subnet this between accounts and guests. So that I'm just going to clear the screen so that we can run through it again. All right, so we're back. So for sales, we've already assigned 192.168.1.0/25 for marketing. We have assigned 192.168.1.128/26 for accounts and guests. We have 192.168.1.192/26. And we have to further subnet. So again, our /26 would be 26 once. So we have 11111111 first octet, 11111111 second octet, 11111111 third octet, and that's 24. So we have 11000000 last octet. Again, once subnetted into 30 hosts, if you want to find the number of host bits, we're going to start by finding the smallest power of 2 that is greater than 30. And that would be 2 multiplied by 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. So, and 32 is greater than 30. So we count 1, 2, 3, 4, 5, which is 5. So we count number of host bits right now, we have 6. And that means that if we make one other network bit, we can further subnet it And using another network, it means that the subnet mask will be 27. Again, don't forget that you can only express this in terms of dotted decimal. And in terms of dotted decimal, our /27 would be 255.255.255. Here we have 31. So it would be using our placeholders. We have 128, 64, 32, 16, 8, 4, 2, 1. And we have 111.0.0.0.0.0. So if we could add that together, we're going to have 128 plus 64 plus 32, and that's equal to 224. So our subnet mask would be 255.255.255.224, or what we would just say is a /27. And to find the number of hosts, we know that our number of host bit is 5, and 2 raised to the power 5 is 32. So we're going to have an increment of 32 from 192. So it's going to be 192.168.1.92 for the first network. And the next one would be 192.168.1.224. Here, our broadcast address would be 192.168.1.223. And here, our broadcast would be 192.168.1.255. So we have been able to subnet our corporate networks into 4 different subnets with different host numbers. So they have different subnet masks. So our new addressing scheme would be like this, where we have 192.168.1.0/25 for sales, and it's going to start from 0 all the way to 127. Here for marketing, we have 192.168.1.128, and it's going to start from 128 all the way to 191. And here we are going to have accounts for 192.168.1.192/27, and that will be 192 all the way to 223. And for our guests, we're going to have 192.168.1.224/27. So going from 224 to 255. So we've been able to unequally divide the network that has 256 addresses into subnets based on the requirements that the subnets have. So we started off this video by looking at the IP addressing troubleshooting scenarios that you may encounter on the ICND1 exam. And then we wrapped it up by looking at the variable length subnet mask. Thank you very much for watching.